This is the start of a new unit on financial applications. So there's a few lessons in this unit, and probably the most practical unit of the year, other than perhaps a sequence in the series. Um, but we're going to actually explore or expand on series, specifically geometric series, to understand how that applies to financial applications. So at the start, we'll talk about simple compound interest, and then eventually we'll talk about annuities, um, what an annuity is, and then how to calculate for different annuities. So the first lesson, I'm going to combine the first two sections into one, only because the concepts themselves are pretty simple, no pun intended, and something that you might be already aware of or understand, especially if you've done grade 9 business. I'm sure in that course when I taught it, we did talk about things about interest and things like that. So let's just start with a small example to sort of highlight one um, concept of interest. So here we have Michael. He deposits $1,000 to a bank account that pays 6% simple interest per annum. So per annum is short for per year. So we're going to calculate how much money Michael will have in his bank account, assuming that he makes no more deposits or withdrawals after 1 year, after 5 years, and after 10 years. So in order to calculate interest, it's really the formula for interest is I is equal to what we call the principal, or whatever amount that's invested, or in this case deposited, times the rate. So in this case, the amount of interest is the principal is $1,000, and he's earning 6%. So it's a percent. We need to convert that to a decimal. So in that 1 year of interest, he's going to earn $60. So 1,000 times 0.06 is $60. So how much money does he actually have in his bank account? So after 1 year, he has $1,000 plus $60, and he's going to have basically $1,060 in his bank account after 1 year. Well, what happens in the second year is, and the idea of simple interest is, you get paid interest on your initial deposit or initial amount in your bank account. So in the second year, again, he's going to earn $60. So basically what we're discovering is that after 5 years, he's going to have $1,000, and every year he earns $60. But since this 5 years has gone by, he's going to earn $60 5 times. So that's going to be $1,000 plus 60 times 5 is 300. So after 5 years, he's going to have $1,300 in his bank account. So we could do the same thing after 10 years. So what we're sort of discovering is that with simple interest, he's earning the same amount of interest every year. So whatever that amount is, we just have to multiply it by the number of years. So in this case, let's do this separately. Let's do the interest. So in this case, the interest is going to be the principal times the rate. And what we discovered is the formula of time. So time in years. So his interest is actually 1,000 times the rate, 0.06. In this case, times 10 years. So here, 1,000 times 0.6 is $60 times 10. So that's $600 after 10 years. So his total amount of money he has in his bank account is going to be $1,000. There's his initial deposit plus $600. So that's going to be $1,600 he has in his bank account. So, I mean, that's the cool thing about interest. It's really earning money without doing any work. Basically, the bank is paying you for them to use your money. You can think of it another way. You can think of it. Sometimes people borrow money or they take a loan from a bank. So really, when we deposit money, Another way you can think of it is that the bank is actually taking a loan out from you. And in order to use your money, they're paying you interest. So it's kind of like free money. So in this case, after 10 years, Michael earned $600 without lifting a finger. That's what the beautiful thing about interest is. So the reason why I really like this unit and making sure that try to get this in for the grade 11s is a bit of appreciation in terms of finances and how important it is to sort of start early, and how the calculations and how the math actually works, so that you can sort of take advantage of it. So this the first lesson is really heavy on concepts and definitions. So that's what we're going to go through for the next little while. So our success criteria is we need to define and understand these certain terms. So one we already talked about is principal. Another way that we can think about that is sort of our initial investment. And another term that's actually be used later on once we get to annuities is a present value. So it's really the same idea, principal and present value. And then the next thing we need to sort of understand is the concept of future value. And as simple as it sounds, that's really the essence of this entire unit, is understanding the value of money. But the value of money has different perspectives. The value of money now, how much is this something worth now, as opposed to how much something is worth later on, or how much an investment is worth later on or in the future. So an example that we just had, we could think of the present value was that initial deposit of $1,000, and then after 10 years, so again looking into the future, that's what we kind of see. That's what we can define that $1,600 is that future value. In this lesson, we're going to understand the difference between simple and compound interest. And then basically we're going to be able to do some calculations on that. So if we're given the principal, we can calculate the future value of both simple and compound interest. Although, I'll be honest, simple interest is not that interesting. Again, no pun intended. But we're going to look at the compound interest situation. In reality, right now, banks do not charge simple interest, nor do they pay simple interest. Everything is done with a compound interest formula. But in order to sort of understand where compound interest formula comes from, we need to sort of understand or know the concept of how simple interest works. So just to summarize what we did above, to calculate the total investment or a loan amount. So again, depending on the perspective, you could look at it as investment or you could look at it as a loan. We're going to look at what the future value was in a current simple interest situation. So as we saw above, we saw that the future value, and really this formula applies to no matter what type of interest is being paid, no matter how it's calculated. Really, we look at the future value as really what was our initial investment or initial principal, and then we're going to add how much interest on that was earned. And really that's the basic formula of understanding principal and interest. Unless otherwise stated, the interest rate is assumed to be per year, or we'll say per annum. In fact, through this entire unit, the interest rate we are given is going to be per annum. Hopefully I remember to say that every single time, but if I forget or if a question forgets to say that, the only type of interest that we will ever do in this unit is interest rate that's based on per annum. So we sort of went through these definitions already, but we'll go through them again. So principal or present value. So that's a sum of money that is to be invested or that's to be borrowed. And then the future value is the total amount of an investment, or think of it as a loan as well, after a certain period of time. So for example, if I took out a loan now for $5,000 and eventually after 10 years I pay back that loan, I might have paid back altogether something like maybe $8,000. So that's what we're talking about. The future value of that loan is really $5,000 turned out to be $8,000. Okay. From a bank's perspective, you could think of it as they invested $5,000. In other words, they gave me $5,000 because and they're investing it because I'm paying them interest. And at the end of 5 years, I can't remember what I said, or 10 years, I owe them $8,000. So essentially, we do that straight calculation. The amount of interest that they actually earned was $3,000. The future value, which was $8,000, minus the principal value or principal or present value, which was $5,000, and the difference is $3,000. So it doesn't matter how the interest is calculated. Just from that basic formula, we could see that the interest earned in that case was $3,000. So we looked at this one little formula where interest, in terms of simple interest, is really the principal times the rate and times the time. In this case, the rate, the R, is the per annum interest rate, and T is time in years. So we could sort of have a formula of future value is the principal plus the interest, but we just see the interest is same as principal times rate times time. And then we could sort of factor out the P, and our equation actually becomes principal times 1 plus R times T. So just a reminder, you always need to convert the interest rate to a decimal. The interest rate is always a percentage. So to convert a percentage to a decimal, we need to take that value, take that percent and divide by 1,000. So let's look at an example. Sherlock invests $10,000 at 3.5% annum with simple interest. How long must he wait for his investment to grow to $13,000? Well, we tackle this problem by just using our equation. So here, future value is equal to principal times 1 plus R times T. So whenever we're going off solve an equation, I always like to go back to my question, find out what information I'm given, and sort of map that to what variable is that in my formula, assuming that the information is relevant. So here we're given $10,000, so that's really my present value or my principal. 3.5% per annum, so that's my rate. So I'm going to convert that to a decimal right away, 0.035. And how long must he wait to investment to grow to 13,000? So that in this case is my future value. So we got my future value, my principal, we got the rate, and we don't know what the time is. And unfortunately, that's where we're being asked to calculate how long must he wait. So we need to figure out what time is. So here we're going to do 13,000 is equal to 10,000 times 1 plus 0.035 t. So we need to figure out how many years he must have to wait. So we divide both sides by 10,000. So here we get 1.3 is equal to 1 plus 0.035 t. Now we're going to subtract 1 from both sides, so we get 0.3 is equal to 0.035 t. And then we need to divide both sides by 0.035. And we're going to discover t is going to be roughly 8.57. So the actual answer in this case is not 8.57. So because with simple interest, interest is paid after the year, so it has to be an integer. So here, in this case, 8 years is not enough. It's going to be shy of 13,000, not exactly how much. So in this case, we have to wait till after the 9th year when we get that final payment of interest to get us past 13,000. So therefore, Sherlock must wait 9 years to have at least 13,000. So that's the tricky part about this case, is that he's not going to have exactly 13,000 after 9 years. In this case, he's going to have a bit more. So let's go off and look at another situation where we talk about compound interest. So what's the notion of compound interest? Well, let's go back and look at this example that we had to start. So after the first year, Michael originally started with $1,000. Bank paid him $60 because they're really borrowing his money and they're paying him interest. So after 1 year, he has $1,000 plus $60. So Michael was a bright dude, and he would go to the bank and says, well, you know what? After 1 year, I have really $1,060, but you're only giving me interest on $1,000. Like, why would I not get interest on the $60? And the bank goes, well, because you only invested $1,000. But then Michael's smart and he goes, well, yes, but then you gave me $60 and that $60 is still in the bank account. So really you should be giving me interest on that $60 as well. And the bank goes, well, you know what, you got a point. That $60 is yours, it's not ours, it is yours. So in theory, yes, we should be paying you interest on top of that interest. And that's the idea of compound interest, is interest on top of interest. That's why the word used is compound. So let's look at that situation and see how that looks like. So when I talk about the year here, it's sort of like after year one or during year one. So at the beginning, Michael has $1,000. And well, how much does he have at the end? Well, because we're doing things in increments, remember we have future value is equal to principal times 1 plus R. But because we're looking at it every year, what's happening every year, the time is always going to be 1. So our formula simplifies to really 1 plus R. So in this case, R is 6%. So let's write down the formula here as principal times 1 plus 0.06. So let's just do the calculation right away. So it's going to be 1.06. So after 1 year, what's his balance? So here we say his future value is going to be the principal, in this case, which was $1,000, times 1.06. And a lot of us, whenever we do this, we want an absolute number. We want to do the calculations. We pull out a calculator, and just as we discovered above, he has $1,060. Well, for the next year, at the start of year 2, what does he have in his bank account? $1,060. But what I'm going to do is I'm going to resist the temptation to sort of calculate that. And I'm going to say that at the beginning of year 2, he actually has $1,000 times 1.06. So I'm not actually going to calculate it. I'm just going to leave that expression there. And this is why. Because what we're going to do is we're going to calculate how much does he have after year 2. Well, again, our future value is a principal times 1.06. But in this case, our principal is what we started off with. So in this case, that is 1,000 times 1.06. So I'm going to put that in square brackets just to indicate that it's principal. And then we're going to multiply by 1.06. So that was this part over here. Oops, I messed up the other line, so let me not do that. Let me try to find like that. Okay, so really, what is this equal to? Well, we simplify this. This is 1,000 times 1.06 to the power of 2. Wow, going on to year 3, what's his starting amount? So again, I'm not actually going to calculate it, but it's really 1,000 times 1.06 squared. So that's his principal for that year to start. So here, the future value is going to be 1,000 times 1.06 squared. So I'll put that in square brackets again to indicate that's the principal. And here we're going to multiply by 1 plus R, in this case 1.06. And in this case, we're going to simplify that. That's going to be 1,000 times 1.06 to the power of 3. So we're starting to recognize a pattern, is that really the year, how many times is earned interest, is really our exponent to the 1 plus r. So starting at year 4, we have 1,000 times 1.06 to the power of 3. That's where the balance at the start is. So the future value after year 3, and I'm just going to write it out, is going to be 1,000 times 1.06 to the power of 4. And we continue this pattern. And we discover after year 5, it's going to be 1,000 times 1.06 to the power of 5. And in this case, I just do want to work it out because I want to do a comparison. So this is going to be $1,348.85. We plug that in the calculator. And if we sort of continue the pattern, we discover after 10 years, well, at the start of the 10th year, he would have earned interest 9 times. And then after the 10th year, we're going to see that his future value is going to be 1,000 times 1.06 to the power of 10. In this case, we put that in a calculator. That's going to be, oh, I miscalculated. Sorry, my bad. So after year 5, it was 13,038.23. And after 10 years, so 1,000 times 1.06 to the power of 10, that's going to be $1,790.85. So we can compare back to our simple interest is sort of the power of compound interest. It doesn't look that great. In fact, after year 1, it really makes no difference whether it's compound or simple interest. It's $1,060. At year 5, if you remember original example or to start, after 5 years, Mike would have earned $1,300. So in this case, it was an extra $38.23 after 5 years. Does it seem like a lot? It isn't a lot, but it does add up, and it does make a significant difference as long as you allow that interest to grow. And we see that once we get to year 10. So just another 5 years later, his value is $1,790.85. This is compared to $1,600 that we have just with simple interest. So even after 5 years, this is an extra $160. So that, what grew from 38 to really now it's an extra $160. And if we sort of continue this pattern, let's say after 15 years, after 20 years, and this is the power of exponential growth, is that this value grows quite significantly. Okay, so that's a cool thing. So again, we're letting interest work for us. That's the financial term that we use because we're letting interest go on top of interest. So that's how the compound interest formula is sort of derived. So let's talk about that. I didn't give it a formula here, but really we could say the compound interest is future value is equal to principal times 1 plus r to the power of n, where n is the number of years. Okay? Well, Michael is a pretty smart dude because basically he started going off and he says, you know what? I know I could do better. So banks started offering savings, if you want to call it that, where, in order to be competitive with one another, all banks were the same. Says, well, no, we could pay interest more than once a year. So, for example, instead of paying at the end of the year, they'll say, you know what, we'll pay you interest twice a year. So maybe after 6 months, and then after 1 year, we'll pay you interest. Well, it might sound like kind-hearted of banks to do that, but in reality, what was going on was that they're charging people that type of interest as well. So when you borrow money from them, they're not going to say, well, you know what, we're just going to charge you interest just once, and that's at the end of the year. This is no, we're going to charge you interest on a regular basis. So maybe every month, every 6 months, whatever it is, you sort of negotiate those rates. So what happens is that So for example, if you had 6% per annum, that was your interest rate, and they said they're going to pay you interest twice a year, they're not actually going to pay you 6% each time, because that's a significant amount of interest every single time. What they do is they actually take that interest rate and actually divide it by 2. So in this case, if they say they're going to pay you interest twice a year, each of the interest payments would be 6 divided by 2, in this case 3% each time. Which kind of makes sense, because they're saying we're going to give you 6% through the whole year, but since we're paying you twice, we're just going to split that up into 2 interest rates, really, so 3% each time. So it gets really complicated, because it could happen more and more times a year. So here's a large table, and so you have to know these terms. So you could get paid interest annually. So this is what we call compounding period, how often the interest is paid in a year. So it's annually, that's one time a year. Okay, so there's another variable called I, which is really, you can think of it as the effective interest rate, or as the actual interest rate that's used on each of the calculations. Is that, well, if it's annually, it's no different than the compound interest equation we just did. So I is just the same as R, and N, in other words, the number of total interest payments we have, is just the number of years. Then we get into more complicated situations where you could be compounding semi-annually. So semi-annually means it's twice a year. And so that means your effective interest rate is really your interest rate per annum divided by 2. Because we're doing it twice, so we're going to split that interest rate twice. But what happens is your number of payments really doubles, so it's the number of years times 2. So I like to, I wish there was a variable that's introduced somewhere in a textbook. I'll call it C, short for maybe compounding period. What we're going to discover here is that I is really our interest rate divided by the number of compounding periods. And here, the number of total interest payments, N, is equal to how many years we have. So that was T, that was our original variable for time, times C. Okay, so one place we divide by C, the other place we actually multiply by C. So quarterly, we're doing it 4 times a year. Monthly, 12 times a year. Weekly, it's 52 times a year. And if you can find a daily interest savings account, that's pretty awesome, because they pay you interest actually 365 times a year. In other words, they pay you daily. Of course, the interest rate that you're given is very small, but because of exponential growth, this actually makes a pretty big difference. So again, R is the actual annual interest rate, or interest rate per annum, and N is the number of total interest payments. So we sort of convert our compound interest formula that we had up here. And I guess maybe I shouldn't have used N. Maybe I should use T, since in this case it was strictly for time. So 1 plus R to the power of T. Well, our general compound interest formula here now is, and I've used PV this time, because I want to start using PV more regularly, because once we talk about annuities, it's going to really talk about present value all the time. So here we're going to have the future value is the present value plus 1 plus I. So I again is R divided by C, and to the power of N, and again N is T times C. So that's your general compound interest formula. So let's look back at what Michael's done. So Michael has actually found another bank that actually pays him same amount of interest per annum, but this time it's compounded monthly. So let's calculate how much money Michael will have in his bank account after 1 year, after 5 years, and after 10 years. So after 1 year, well, let's write out some of our variables off to the side. So we know that the present value is 1,000. The R, in this case, is 6%. Well, it's compounded monthly, so I'm going to use my variable c to say that this is actually 12, and the t is going to be different for every single time. So let's do let's calculate I first. So I is going to be 0.06 divided by 12, which is 0.005. And our first example, we have time is 1 year. So that implies that n is n times t, c times t, which is 12. So in order to do a calculation here, we say that the future value, so let's write our formula, is the present value plus 1 plus I to the power of n. So in this case, it's 1,000 times 1 plus 0.005 to the power of 12. And we discover plug that into a calculator, and that's actually a tricky part about this unit itself, is making sure that we can plug this into a calculator properly with the exponents and everything. So after 1 year, he's earned $1,061.68. So compared to the normal interest, whether it's simple or compounded annually, he's earned an extra $1.68. Not bad for doing nothing really, other than shopping around. So after 5 years, let's write the formula again, 1 plus I to the power of n. So in this case, I hasn't changed, but since t is 5 years, in this case, that implies that n is 12 times 5, which is 60. So here it's going to be 1,000 times 1 plus 0.005, which is 1.005 to the power of 60. And after 5 years, he's earned $1,348.85. So much better than simple interest of $1,300. And if we go back and look at our compound interest annually, that was $1,338. So here, just by shopping around, I know it doesn't sound a lot, but after 5 years, he's earned an extra $10. But this is where it makes a big difference as we let it grow. So really, I'm going to advise you, as you think about your financial future, to invest early and just to let it grow. And this is what the power of compound interest does for us. So future value in this case is going to be present value times 1 plus I to the power of n. So here t is 10. So that implies that n is going to be 12 times 10, which is 120 interest payments he's going to receive over 10 years. So this is going to be 1,000 times 1.005 to the power of 120. And here, after 10 years, he's going to earn $1,819.40. So compared to simple interest, not even close. $219 more. But compared to compound interest annually, which is $1,790, so this is about approximately another $30 more. So again, that doesn't sound a lot, but for doing nothing and earning an extra $30, I'll take that any day. And notice that here, the principal amount is actually pretty modest, $1,000. This would see a much more bigger difference if the principal amount was, let's say, $10,000, $20,000. The higher our principal is, the faster this is going to grow. Okay, and hopefully you can see that in some of the homework, speaking of homework, that's going to be assigned. Okay, so this is the notion, just to start us easy, of at first the simple interest, but more interestingly after compound interest, but really getting used to the language, getting used to the variables, and getting used to the calculations, because that's going to be really important when we talk about annuities, which will be in a couple of lessons.